A particle M is suspended from a point P on a ceiling by means of a light elastic string of natural length d and elastic constant 49 m over d. It is pulled down a distance 8d over 5 below P and released from rest. Show that it will perform simple harmonic motion as long as the string remains taut. What I'm going to do in this question is I'm going to do what we always do, and I'm going to show you that we might encounter a problem. And then I'm going to show you, once we hit that problem, how to go about getting rid of the problem. Okay? So we're going to do everything that we normally do, but we're still actually going to encounter a problem. Okay? So what happens here is we just set up our system. We have our point P from the ceiling. We have our natural length, so our string, which we'll put in black here. Our string comes down its natural length. Okay, and then it's pulled down a distance 8d over 5. Now 8d over 5 minus d is 3d over 5. So the extension is 3d over 5. Okay, so extension is where it becomes dotted. That's going to be 3d over 5. Okay, and our particle of mass m is pulled down a distance 8d over 5 below P and released from rest. This doesn't mean it's the equilibrium point, right? It says it's released from rest. Show that the shell will perform simple harmonic motion as long as the string remains taut. So this is 8. This part here is d, and this part here is 8d over 5. Now, what we currently don't know is we don't know anything about where is the equilibrium position. We don't actually know that at all. Okay, so without bringing the 8d over 5 into play, what we probably should do at the moment is find out where is the equilibrium position. Okay, so if this is defined as d, we might define the full thing as LE, the length of the equilibrium position. Okay, so let's find out what the force is. Okay, so force up versus force down. So at EP, it's force L, sorry, not force L, force up equals force down. Okay, force down is very easy to do. It's going to be the particles of mass m, which means it's mg going downwards. So force down is most definitely mg. Now force up is more complicated. It's k times L minus L0. We defined L as LE. The reason being is D is already taken. Okay, so we can say K is, what's the value for K? 40. Sorry, okay, so 49 m over d. So 49 m over d multiplied by LE minus L0. What's L0? D equals mg. Now let's see what we can cancel out. The m's can cancel because they're being multiplied on both sides. We can also multiply in, so we're going to get 49 LE divided by d equals, the two d's will cancel and you'll just get a minus 49. G on its own is 9.8. Then you're going to get 49 LE divided by d. What's 9.8 plus 49? 58.8. Now LE therefore has to be 58.8 d, all divided by divided by 49. What's 58.8 divided by 49? 1.2. So it's 1.2d, also known as 6d over 5. Okay? So what we've proven here is that the natural, its equilibrium point is 6d over 5. Okay? So 6d over 5. That's its natural length. Its equilibrium point. We'll just shade this in red as well. So at its equilibrium point where the forces are balanced, which is here, that is 6d over 5. And we know that it's 8d over 5, isn't it? Now this is what I did earlier with the 3d over 5. That actually means nothing. That's actually just how far it's away from its natural length, which isn't how we do these questions. So what we're going to be looking at here is that it's its current length when it's released from rest. It's always defined as its distance away from equilibrium. So that's going to be 6d over 5. Take them away from each other. You know, your amplitude is going to be 2d over 5. So you're going to pull it down a further 2d over 5 further down. So this here is going to be 2d over 5 away from your equilibrium point, EP. Okay. Now that that's done, show that it will perform simple harmonic motion as long as the string remains taut. To show that it performs simple harmonic motion, you have to do a general extension from equilibrium, x. Okay? So currently speaking, my current length for this part of the question is going to be this. It's going to be, you have P there, I have my string going all the way down. That's its equilibrium point, and then I'm going to have it going a further extension x. So it's been extended x, its equilibrium point was here, which is 6d over 5 away from P. Okay, so time to set up our system, okay? Now, net force, because it's been extended below its equilibrium point, net force equals force down minus force up. Okay, net force is going to be it's ma, isn't it? Because the particle is m. So ma equals force down. What's the force down? mg, which is 9.8 m, minus force up. Force up is going to be the k value. What's the k value? 49
m over d.
M over d. Its current length is what's a 6d? So 6d over 5 plus x is its current length. 6d over 5 plus x. And what's its natural length? D. Okay, let's have a look here. What usually happens in all these questions? They get cancelled, and what happens when they get cancelled is we're left with nothing but the x value. Let's see if this happens. Okay, first and foremost, all the m's can disappear, can't they? Because m is being multiplied by everything on this line. Next thing, a equals g, which is 9.8 minus now what's 6d over 5 minus d?
D over 5.
D over 5. So you can just quickly do a quick rub out there, and now that's your d over 5 plus x. Multiply in 49 divided by 5 is 9.8. And actually, as it turns out, they actually do cancel. So although I was saying at the start I thought there might have been a wrong way of doing this, there's a real fancy way of doing it in the book, right? As it turns out, they're actually going to cancel anyway, so the method we've been using all along is perfect. Okay, so 49 over 5 turns to your 9.8, and then we're going to get minus 49 x over d. So what's a 49x over d? That's perfect. The two of these will cancel out. A now equals minus 49x over d. Now, if we look at this, what we can get is it does undergo simple harmonic motion because it's minus omega squared x. Okay, and then omega squared equals 49 over d. Therefore, omega will equal 7 over root d. Because square root of 49 is 7, square root of d is root d. Okay, so we've done that successfully. And find in terms of d when the string becomes slack for the first time. When does a string become slack, guys? Not when it's at equilibrium point. The string only ever becomes slack when it makes it back up to d. When it makes it back up to the natural length. Okay? So let's reevaluate our system at the moment. To reevaluate this, let's go on it. That there. Okay. What we started at the start question is we had our point from P and it wants it to come slack. We argued that this here, or we didn't argue, we proved that the equilibrium point is 6d over 5 all the way down. Okay. We then proved that the amplitude, we proved that the amplitude is to 60 over 5. We proved that the amplitude of its motion is 2d over 5 because it was pulled down a further 2d over 5 to give you 8d over 5 in total. Okay, now it's released from rest, and what it has to do is it has to travel. I'll also put in the normal distance as well. The point where it becomes slack is a distance d. You happy enough with that? Alright. Now, can anybody tell me what is this distance in here? From here to here? It's d over 5. So you have to pass your equilibrium point and go all the way up d over 5. You also have to travel 2d over 5 to get your equilibrium point, and then you have to travel d over 5 further up. We have to find out 2 times. We have to find out what t1 is, and we have to find out what t2 is. You can't do it in one go. Why can I not do it in one go? X is defined as not the total distance travelled, is defined as your distance travelled from equilibrium, or your displacement from equilibrium, given a starting point. So what we can do is we could figure out what is the time taken to go from here to here. Figure that time out first. Then you're starting at equilibrium point. If you start at equilibrium point, what is the equation? A sin omega t. Now, this here is an amplitude, right? How long does it take to travel one amplitude? We did this the last day. It's A up again to complete one full cycle. A up, A down, A down. To complete one full cycle contains 4 amplitudes. So the period, the time taken to do 4 amplitudes is 2 pi over omega. Okay? So what we need to do is we need to find out what d over 4 is. Okay? So excuse me in a second. Just have to reread the question. Find in terms of d when the string becomes slack for the first time. So he does it when x equals d over 5. Okay, I'm going to try it a different way than that. I just want to try it my way first. Okay? So, what I'm going to do here is the following. I'm going to do, the time taken is a quarter of the amplitude, alright? Is a quarter. We went over that already. So what I'm going to do is, it's a quarter, 2 pi over omega. And what's 2 pi over omega? Omega is 7 over root d. And what that will become is 2 pi divided by 7 multiplied by root d divided by a quarter. And this will become, anybody know this? It's going to become pi root d over 14. That is T1. Is everybody happy with T1? Now I'm going to do T2. T2 is going to be A sine omega t. Okay, which is going to be A sine omega t, and we know that x, this is T2 here, so we have to find out what t is. So that's x equals A sine omega t. What did we say x was for the second part? D over 5 equals A. A is 2d over 5 sine 7 over root d. 7 over root d times T2. Okay, let's figure this out. The 5's will cancel, the d's will cancel. It's equal to a half. Sine all of this equals a half. Okay. Now, what we can get here is the following. We can get that sine inverse a half. Anybody? In radians. So sine inverse a half is pi over 6. This is pi over 6. Pi over 6 is now equal to 7 over root d times T2. T2 therefore is pi over 42 root d. Is everybody happy with that? Equals T2. Now, what you need to do is you need to add T1 and T2 together. Now the trick is to adding T1 and T2 together is just ignore the root d and use your calculator. So we're going to get pi root d over 14 plus pi root d over 42. What we can actually see there is that there is actually very simple common denominator there, isn't there? Just multiply it by 3. So what we can do is we can just multiply that by 3 on the bottom, multiply it by 3 on top, and what we should get now is we will get 4 pi root d over 42, cancel and divide by 2, and we're going to get 2 pi root d all over 21, which is the correct answer. I will, however, just show you one modification on that answer. There is another way of doing this. You can break it up into 2 parts, okay? But there was actually another way. You could actually use a minus displacement. Alright, I'll show you that now. What I was saying earlier was you couldn't use the total distance travelled. Just keep that answer in mind. This is a much shorter way that only requires one time. Okay, so this way here would be, what you're doing is you're saying that the amplitudes, this will take 2 minutes, okay? The amplitude is, you're starting off at the extreme point here. And what you're going to do is, by the end of this question, your displacement is over the other side. See the way you're currently over one side of the equilibrium position. By the end of this question, you're going to be x equals minus d over 5 over the opposite end of equilibrium. That makes it a negative. We can start off our position at the equilibrium point, which is our extreme point, which is a cos wt. X therefore is minus d over 5. A is 2d over 5. Cos is, that's cos omega. What's omega again? 7 over root d times t. And what you can figure out this time is that, the d's will cancel. The 5's will cancel. Can somebody get me cos inverse minus a half? Now, was it?
2 pi over 3.
2 pi over 3. Okay, 2 pi over 3. What's 2 pi over 3 in, what's 2 pi over 3 in degrees? Remember, pi is 180, so just
Yeah, okay.
multiply 180 by. So they took 120 degrees, didn't they? Is that right? 2 pi over 3 is 120 degrees. So just keep that in mind. This is why some people might find this confusing. ASTC. The first time it's negative, yeah? The first time it's negative, you start your clock here. When is cos negative first? In the sine quadrant. That's why you take 2 pi over 3 as opposed to the answer in the tan quadrant. Do you got it? So therefore, the answer in the tan quadrant would be when it's on its way up and then on its way back. But we don't need to make it that complicated. Therefore, 2 pi over 3 equals 7 root d over t. Bring the 7 down and we get the same answer. So the advantages of the first way is it's longer, but there's no messing around with negative angles and what quadrant you should take. The advantage of this way is that it's faster, but the disadvantage is some people might get mixed up with the quadrants. Okay guys, good class. For homework, what I'd recommend you do